Alright, RC integrators. RC integrators are the way shifting network with the competent communication with the radar with the computer with the harmonic component content with the square wave is made up of the odd multiple of fundamental frequency, therefore the significant harmonic for those who have an effect with the circle high with the 50 to 60 times fundamental frequency will present with a wave of the capacitor will offer the reactant for the capacitor reactant will offer, the capacitor will offer the reactant for the different magnitude for each of the harmonic. The capacitor reactance is equal to 1 over 2 times pi times the frequency times the capacitation. This means the voltage drop of the curve of the capacitor each of the harmonic frequency present will not be the same with the two low frequency capacitor will offer the large opposition provided the large voltage drop of the curve of the capacitor with the high frequency reactive of the capacitor will extremely small with the curve of the small voltage drop of the curve of the capacitor the no different than when it was when was the case for the low or the high pass filter is discriminated with the present within chapter 1. But the voltage component of the harmonic is not developed with the curve of the resistance the curve of the reactance of the capacitor will develop the curve of the resistor. It will observe the crisscross of the voltage level of the harmonic amplitude of the phase relation for the curve of the capacitor is not same with the original frequency input, therefore the perfect square wave will not be produced. The curve of the capacitor should remember the reactance offered with each of the harmonic frequencies. It will cover the change of both amplitude phases of each of the individual harmonic frequencies with respect to the current frequency, the amount of phase, the amplitude with the change of the take of the phase. The curve of the capacitor depending on the capacitive reactance of the capacitor. Therefore, the value of the reactance for the resistance offered with this resistor must also be considered here as their portion of the ratio voltage drop that will help the curve of the network. Circuit in figure 430 will help you show the relation between the resistor and the capacitive reactance more clear with the square with the wave applied with the circuit with 100 volts peak with a frequency of 1 kilohertz. The odd harmonics will be 3 kilohertz, 500 kilohertz, 7 kilohertz. Table 411 show for the value of the capacitive reactance for the resistance offered to several harmonic indicator the approximate value with the cutoff of the frequency. Capacitive reactance equal to the resistance table clearly show for the cutoff of the frequency live between the 5th and 7th harmonic between the two value of the capacitive reactance will equal the resistance. Therefore, all the harmonic frequencies above the 5th and the majority of the output voltage will not be developed. The curve of the output of the capacitor, rather, most of the output will develop with the curve of the resistance. Absent the higher order of the harmonics will cover the leading edge of the waveform to develop the curve of the capacitor to be rounded. Example of this, in fact, is shown in figure 431 value of the capacitance increase the reactance. Say that each of the harmonic frequency will be further decreased by means of the fewer harmonics will develop the curve of the capacitor. 430 show the partial integration circle of the 100 volts and the negative 100 volts of the resistor 25K and the capacitor of 100 thousandths of a microfarad. Show the pair partial integration, and also the harmonic, the fundamental with the capacitor reactance and resistor. Harmonics are not effectively developed with the curve of the capacitor must develop with the curve of the resistor shaft allow the Kirchhoff of the voltage level of the pattern of the voltage waveforms the curve of the resistor and capacitor waveforms the curve of the resistor capacitor would add graphically with the result would be exactly duplication input square wave of the capacitance and increase the sufficiently integration for the input signal take for the place for the output of the capacitor curve of the capacitor. Example of completion integration shown in figure 432 with the voltage voltage capacitor, the effect of the curve of the insignificantly decrease of the capacitance reactant with the same effect of the will take place to decrease the value of the resistance integration that takes place with the resistor's RC circuit with output taken across the capacitor. Figure 433 show the integration resistor capacitor times 10 equals 10 times the period of the voltage input. The amount of the integration dependent on the value of the RC, the amount of the integration of thus depend on the time of the constant of the circuit. The time of the constant circuit should be made at least 10 times greater than the time of the duration. Initial input falls for the integration curve. The value of the 10 is only an approximation. Well, the time constant in the circuit is 10 or more time with the value of the duration of the input pole. The circuit is said to be pole for the long time of the constant. The time of the constant is longer than the capacitor does not have the ability to charge the instant of the value of the applied voltage. Therefore, results in long slipping integrated waveform. Your RL integrators. The RL circuit may be used with the adding of the integrated circuit. The integrated waveform must be obtained with the series of the RL circuit, making the output across the resistance of the characteristics of the inductor show the first instance of the time with which they apply with the current flow through the inductor. Minimum voltage to envelop the curve of the maximum. Therefore, the voltage value of the voltage drop the curve of the series resistance first instant must be 0 volts. Because if there is no current flow through this time, the passive current flow through the circuit of the voltage drop the curve of the resistor. Since the circuit has a long time constant of the voltage curve of the resistor, not respond to the rapid change of the voltage of the input square wave. Therefore, the conditions of integration in the RL circuits are a long time constant for the output taken across the resistor. These conditions are shown in figure 433. 433 show the RL integration waveform. Integration waveform analysis. Either RC or RL circuits have the time constant 10 times greater than the duration input pole. The circuit is capable of the integration. Let's compute with the graphical actual waveform that would result with a long time constant for the 10 time pulse duration, the short time constant 1/10 of the pulse duration, a medium time constant time constant before the long and short. The accurate pull-out value for the capacitor output voltage will use the universal time constant chart shown in figure 434. 434 show the universal time constant chart. A with the curve A with the capacitor voltage of the, on the circuit and the RC circuit. inductor current of the resistor voltage within build up, and B, the capacitor voltage within the discharge, resistor voltage of the capacitor current within the charge of the discharge, inductor current of the resistor voltage on the decay, inductor voltage within the build up of the decay. Alright, you already know that the capacitor charge of the file with the shape of the curve shown in figure 434 with the curve of the maybe you would determine the amount of the voltage across the either component of the shape of the RC circuit along with the time constant fractional part of the time of the constant is known of the voltage across the either component may be determined. Short time constant integrated. The figure 435 with 100 microsecond pole with about amplitude of 100 volts to amplify with the circuit compressed is 100 microfarad capacitor with the value of the resistor of the square wave applied with the square wave. The resistance of the variable resistor is set with the value of the 1000 ohm. The time constant for the circuit is given in the equation. The time constant is equal to the resistance time of the capacitance. So since the time of the constant of the circuit is 10 microseconds for the pulse duration, and the 100 microseconds for the time constant is shorter than 1/10 of the pulse duration of the capacitor charge with the exponential through the resistor. 5-time constant for the capacitor will be in all practical purpose of the completed charge. Add the time constant for the capacitor charge with the 63.2 volt, the second at 86.5 volts, and the third at 95 volts, and fourth at 98 volts, and finally at the end of the fifth time constant 550 microseconds for the capacitor is fully charged as shown in figure 436. Note for the leading edge of the square wave, the taking the curve of the capacitor is rounded off at the time of the constant made it extremely short with the round edge that was become smaller. Square. Or your medium time constant integrated. With the time constant figure shown in 436 can be changed with the increasing value of the available resistor for 435 with the 10,000 ohm, but the time constant will equal to 10 microseconds, 100 microseconds. The time constant is known with the medium time constant value live with the beyond the extreme range for the short and long time of the constant. In this case, the value happens to exactly equal with the duration input pulse for the 100 microseconds, and the output waveform after the several time constant is shown figure 437 with the long sloping rise and fall of the voltage cover the inability of the capacitor to travel the discharge rapidly with 10,000 ohms of series resistance. At the first time instant, the time of the 100 volts is applied with the medium time constant with the circuit with the ITC with exactly with the equal of the duration input with the small with the ITC with the capacitor travel with the 62.2 volts input voltage 100 volts. Therefore, the end of the ITC 100 microseconds the voltage of the across the capacitor is equal to 62.2 volts. However, assume that the 100 microseconds is the lamp. The initial travel of the capacitor has driven the 63.2 volts. The input voltage suddenly drops to zero. The remainder, therefore, for the 100 microseconds of the capacitor now driven the charge 100 microseconds for the discharge of the time of the 100 microseconds of the ITC, the capacitor will discharge 63.2% of the total of the 63.2 volts is charged at the value of the 23.3 volts during the next 100 microsecond of the input voltage will increase from 0 to 100 volts. The instantaneous the capacitor will again charge the 100 microsecond of the ITC with the voltage available to charge, but the difference between the voltage applied with the charge of the capacitor 100 times minus 23.3 volts or 76.7 volts. The capacitor will be only able to charge the ITC with the charge of the 63.2 with the 76.7 with the 48.4 with the total charge of the capacitor and the 300 microseconds will be equal to 23 plus 48.4 volts or 71.7 volts. Note for the capacitor voltage at the end of the 300 microseconds with the grade with the capacitor voltage at the end of the 100 microseconds with the voltage at the end of the 100 microseconds with the 63 volts with the capacitor voltage at the end of the 300 microseconds with the 71.7 volts then increase to 8.5 volts. The output waveform of the graph of the voltage of the current voltage capacitor of the waveform produced for any many cycle of the input signal of the integrator of the capacitor will charge the discharge of the step by step of the manner until the final charge discharge above the below the 50 volt level. The 50 volt level is controlled by the maximum amplitude symmetrical impulse of the average value which is 50 volts. Your line time constant integrated with the resistance of the circuit figure 435 increase with the 100,000 ohm of the time constant for the circuit is 1,000 microsecond with the time of the constant with the 10 second of the pulse duration input pulse. Therefore, the long time constant circle the shape of the output wave the cross of the capacitor shown in figure 438. Shape of the output wave the characters of the long sloping rise with the fall of the capacitor voltage. Figure 438 shows the square wave applied with the long time constant integrated voltage. At first time integrated in the first instance of the 100 volts applied with the long time circuit, long time constant circuit is the first the value of the charge of the capacitor and for the first 100 microsecond of the input signal is can be found by the universal time constant chart figure 434. With assume that the line is projected above the point of the basic line corresponding with the 0 tenth of the ITC. The line will intersect the curve at the point with the percent of the voltage across the capacitor at the 100 microsecond of the density applied voltage for the 100 volt charge of the capacitor end of the 100 microsecond will approximately 9.5 volts. At the end of 100 microsecond, input signal will fall suddenly. The zero of the capacitor will begin to discharge. It will be discharged for the 100 microsecond of the capacitor will discharge 9.5% of the actual accumulated 9.5 volts or 0.9 volts. Discharge of the 0.9 volts of the result of the remaining charge of the capacitor 8.6 volts. At the end of the 200 microsecond of the input of the signal will again suddenly arrive at the value of the 100 volts of the capacitor will be able to charge the 9.5% of the difference of 1 100 plus minus 8.6 of the 91.4 volts. This may also figure with the value of the 8.7 volts must be initial 8.6 of the volts. The result of the total charge of the capacitor at the end of the first 300 microseconds of the 8.7 plus 8.6 of the 17.3 volts. Note of the capacitor voltage and of the first 300 microseconds of the greater of the capacitor voltage and of the first 100 microseconds of the voltage and of the first 100 microseconds of the 9.5 volts capacitor voltage and of the first 300 microseconds of the 17.3 volts included the 7.8 volt capacitor. The charge of the discharge of the step-by-step manner. Finally, in the capacitor charge of the discharge above the below the 50 volt level. The 50 volt level controlled the maximum amplitude square level wave input signal pulse of the average value within 50 volts. We're going to cut the tape there, and we're going to do another tape.